Okay, this time we will learn about what's called alteration method. Or oftentimes it's also called deletion method. So far, what we have been doing is that we randomly generate some object. And then we define some bad events. And then we show that with certain parameter, I mean, if we randomly take this object, and with positive probability, we can avoid those bad structure. I mean, we can get some desired object. Okay, that's roughly what we do. And oftentimes, if we choose this parameter in a certain way and then take a random object, and we get some object, we can show that we can find some object which is almost what we want, but still have some bad structure or bad event for it. And in order to completely remove those, we have to tune this parameter better. That will often give us some words bound on what we want to prove. And it is natural that to consider some other way to get a better bound. Because, I mean, so this is quite close to what we want. It have certain bad structure, but those are not too many. So instead of tuning the parameter in a better way to make the bound worse, we might wonder that can we take this object as random and then can we do something more to get a better bound? That leads to this something called the alteration method. Instead of taking a purely random object, we take a random object and we make some adjustment in a deterministic way, non-random way. So this is alteration, so we call this an alteration method. Using this, we can obtain a better bound on this, better lower bound on the Ramsey number. Because that the previous lower bound we obtained was that E times square root of 2, A2 K over 2, and we can remove this square root of 2. Technically, I mean, this constant is slightly more than 1, but this one is going to 0 as k equals to infinity. So, this is almost square root of 2 times better than the bound before. So here, again, we take number n, which is a number we don't fix now, but which we will later determine. Okay, and now we take x, which is the random variable that counts the number of monochromatic k clicks on k vertices in a random 2 coloring of the edges of kn. So the worst bound with the square root of 2 here, how did we do it? We proved the probability that you get 0 monochromatic k click is positive. So you want to avoid all of them. But here, instead of avoiding them, we want to count them. So we are allowing the existence of certain monochromatic K-clique. So we just count them. And then we want them to be not right. Once we have this random variable, we want to compute the expectation. For that, how do we count it? So this is summation of this indicator random variable, where this C runs over all K vertex subset of the vertices of Kn, and x of C is the indicator random variable. Such that it is 1 or this is 1 if C, and this is a monochromatic clique, and this is 0 otherwise. Then we can compute the expectation. What is it? So we take the linearity of the expectation, you add the probability that each random variable is 1, and the number of choices for C and choose K, you choose K vertices. Once K vertices are given, there are what? K choose 2 edges, all of them having the same color. Is the probability that this happens. This is all of them being red and all of them being blue. So this is the expectation. Okay, and what? Once we have this expectation, then there exists coloring with at most this many monochromatic K-clique. We take such a coloring, and then what? We delete a vertex from each monochromatic K-clique. So there are K vertices in such a clique, and you choose one of them in arbitrary way, and then you delete it. In such a coloring, then what? We are left with a graph with at least n minus n choose K times 2 times 1 minus K is 2. So and most that many monochromatic K-clique, and we delete one vertex from each one of them. So we delete and most this many vertices. So we are left with this many vertices. But it has no monochromatic K-clique. So this provides a lower bound on the Ramsey number, because the number of vertices is here, and then we have a 2 coloring where no monochromatic cliques are there. Thus, the RKK is at least n minus hence K times 2 to the 1 minus H2, which is at least n minus n times E over K to the K to the 1 minus K over 2. So we didn't define what n is, right? So we choose n to maximize this bound. We want a better, good lower bound. So we want to choose n to maximize it. How do we do it? we take this as f of k. So we f of n, and then we take a derivative. Derivative being 0 give you the extremal value. I mean, local extrema, and then that give you a way to maximize this. And then if you take the derivative and then let it be 0, then that's 1 minus what? K times E over K times N E over K to the K minus 1 times 2 to the 1 minus K minus 1 over 2. So K being, consider K as constant and N as variable, you get this. So in order to make this 0, we can set N to be what? It is just the calculus 1 over E times K times 2 to the K over 2 times 2 to the E to the negative 1 over K. And when K is large, this is almost 1 plus 0, 1. So this is almost 1. And we don't gain too much of exactly optimizing this number. So just taking, let N be this number by taking this as if it is 1. So K times 2 to the K over 2 over 2. And this gives you a linear maximization, but it makes the calculation more complicated, and then it doesn't really give you a better bound. So it's enough to take this. Sometimes this kind of a mathematical sloppiness helps to write your proof and then get more intuition and get more understanding. Then what do we get? Then RKK is bigger than N minus NE over K to the K times 2 to the 1 minus K to the 2. And then you just apply this, then it is what? 1 over E times K times 2 to the K over 2 and 1 minus 2E over K. Then this is what? As K goes to infinity, this is 1 minus 0, 1. So RKK is at least 1 minus 0, 1 times K times 2 to the K over 2 over E as desired. So this gives you a better lower bound on the Ramsey number. Okay, let's see one more example of this alteration method regarding the following concept of dominating. We say that a vertex set in a graph G is dominating set. This is dominating if every vertex outside F as a neighbor in S. So this is a useful concept. You can immediately make some situation that it is important. For example, if you have a graph and you want to distribute some resources and put some resources in each vertex so that every vertex can reach the resources in a easy way in one step. Then you want to put them in a dominating set so that every vertex can reach that in one edge. Or you can imagine other situation that these are like streets and then these are location, and you want to put the policemen so that they guard the places and as well as the other place that he can see. And this edge is the relationship that you have a vision on the spot. And dominating set is the good places to put policemen so that you can guide everywhere. And yeah, you can come up with lots of situation where this dominating set is used to concept. And then the question is that can you find the dominating set in a graph? Of course, you can take everything, but can you find the small dominating? And again, the important parameter here is that if you have lots of edges, then your dominating set might be smaller intuitively, because in that case, one vertex can take care of putting one vertex into the dominating set, take care of the lots of other vertices. So maybe the minimum degree is the right concept to consider here. So if you have n vertex graph with minimum degree k that has always has a dominating set of size and most 1 plus log k plus 1 natural log over k plus 1 times n. So you can find you don't have to choose too many vertices. As k goes to infinity, if k is large and this is a constant, this is going to 0. So you don't have to take entire vertex set to get the dominating set. Roughly log k over k fraction, you take them, then it's enough. So again, naturally we form a random vertex subset S in such a graph by what? Including each vertex in this S independently with probability P, which is log k plus 1 over k plus 1. That's the probability. Once we have this S, we take the T. So this is S is random variable, and then depending on this random variable, T is also random variable. T will be determined from S. T be the set of vertices which is outside S that has no neighbors in S. So that's the set of vertices that's not dominated by this S. Then what? Then S union with T is a dominating set. So adding this T is the alteration. You have this random set S. We want it to be the dominating set, but all the vertices here has neighbor here. But some vertices here does not have a neighbor to S. So because of this, S is not a dominating set, but we add them to this S to artificially make it a dominating set. Then we want to, this is dominating set, so we want to, find the expectation number, it's expectation of this side. We want to compute the expectation of the side of this set. So what? Since every vertex, we know that they appear in S with the probability P, expected size of S is NP. So this is easy from the linearity of expectation. Each vertex is paired with probability P, then you add n vertices. And the random variable T, the size of T. So this is the random variable. This is the sum of n indicator random variable. for each random variable, each indicator random variable is regarding whether individual vertices belong to T or not. But when do we have a vertex in T? That's if and only if B and all of its neighbors are not in F, then it's there. You have B and then the neighbor, and none of them are in B. That's right. This has probability and most what? So not in P, not in F, not in F, not in F, not in F. So degree of this vertex plus 1 here. And this is n most or minus P to the K plus 1 because this vertex has degree at least K. It has minimum degree K. And what do you know? This is at most E to the minus P times K plus 1. So we have that from the linearity of expectation, this is summation of these two expectations, and then that's NP plus N times E to the minus P K plus 1. And how did we choose P? P was this. So if you just apply that, then it is 1 plus log K plus 1 over K plus 1 times N. So then what do we conclude? The expectation is this. So there exists choice of F where this is smaller than its expectation, showing that the G contains a dominating set of sides and most this number as desired. So this proves what we wanted. Okay. Yeah, I want to go over one more example of this alteration method. And yeah, maybe I will do it in next video. Okay, see you in the next video then.